Now we are going to discuss about abnormal molar masses in colligative properties. While discussing colligative properties, we discussed how to calculate the molar masses of solute present in the solution. If non-electrolytic solute is used, okay, we get normal molar masses for every solute, because colligative properties are the properties which depends upon the number of solute molecules or quantity of solute present in the solution. So what do you mean by non-electrolyte and electrolyte? So we see the difference between these two. So if I use sugar as a solute or glucose as a solute, it's a non-electrolytic solute. It is not going to dissociate in water. See, if I take sodium chloride as a solute, it's an electrolytic solute which is going to dissolve and dissociate in water. If I take 1 mole of sugar in any amount of solvent, after the dissolution in the solution we get only 1 mole of sugar or glucose. It is not going to dissociate in the solution. But if you take electrolytic solutes, they dissolve in water. Along with that, it also dissociates into 2 ions. Since the colligative properties depends upon the quantity of solute present in the solution, we get abnormalities in the molar masses. Here if I take 1 mole of sodium chloride in the solution, after the dissolution it forms 2 moles of ions. It forms 2 moles of ions. Since colligative properties depends upon the quantity, the molarity as well as the molar mass changes. Now I will give you some examples for these type of behavior of solutes, which is known as dissociation. Electrolytic solutes undergo dissociation in water. Here if I take sodium chloride, if I take 1 mole of sodium chloride in the solution, we get 2 moles of ions. If I take glucose, 1 mole of glucose in the solution, we get only 1 mole of glucose only. If I take aluminium sulfate, Al2SO4 thrice, so how it dissociates? It dissociates into 2 moles of aluminium 3+ and 3 moles of sulfate. Totally it produces 5 moles of ions in the solution. One more type of behavior of solute is association. So association takes place in the presence of non-polar solvents. If I put acetic acid in benzene, it dimerizes. So what do you mean by dimerization? Here I have written dimerization means association of 2 molecules into one molecule. Here if I put 2 moles of acetic acid into benzene, at the end of the preparation of solution I get only 1 mole of acetic acid, due to the association, associate. So dimerization means 2 moles associates to give 1 particle. Trimerization means 3 moles associate to give 1 particle. Tetramerization means 4 moles associates to give 1 particle or 1 molecule or 1 mole. If I take 2 molecules of acetic acid in benzene, but in the benzene what happens? These acetic acid molecules associate through hydrogen bonding like this. Hydrogen bonding is formed between these two, hydrogen and oxygen. These 2 moles of acetic acid gives you only 1 mole of acetic acid as a whole, or 2 molecules will give you 1 dimerized molecule. If you take 3 molecules, if they undergo trimerization, then 3 molecules gives you a set of 1 molecule as a trimer. If you take 4 molecules of any substance or any electrolytic solute, so then 4 molecules give you a set of 1 molecule as a tetramer. So due to this, what happens? Number of molecules decreases. So we expect more number of molecules while adding, but due to this association, number of molecules decreases. Due to dissociation, number of molecules increases. In calculation, what we expect, if you put 1 mole of NaCl, in calculation we also put 1 mole only. But in the actual solution there are 2 moles. So that gives you the abnormalities in molar masses. Similarly, if you put acetic acid, 2 moles of acetic acid, in calculation we use 2 moles, but actually in the solution we have only 1 molecule due to association. Again, it causes abnormalities. Now coming to the formulas, how we get abnormalities, let us see. I'll take elevation of boiling point as an example. Delta TB, elevation in boiling point, is equal to Kb into M, not Kf, it's Kb into M. So what is M here? M is the molality, Kb is constant. M is molality. Molality is equal to what? Number of moles divided by mass in kg, mass of solvent in kg. Now, I take NaCl. If NaCl behaves normally, if it is not undergoing dissociation, how many moles of NaCl is present in the solution? 1 mole only. If you drop 1 mole NaCl in 1 kg of water, so if it is not undergoing dissociation, in the solution we have 1 mole of NaCl only. But NaCl undergoes dissociation. Now, what we have? See, we dissolved 1 mole of NaCl in 1 kg of water. If we do not expect dissociation of NaCl, in calculation also we use number of moles or molality as 1 molal. But sodium chloride undergoes dissociation. It produces 2 ions of Na plus and Cl minus. So now what happens to number of moles? N2 becomes equal to 2. Number of moles increases as well as molality increases. As M increases, delta Tb increases. As number of moles increases, delta Tb increases. As delta Tb increases, what happens to the molar mass of solute? It decreases because delta Tb is in the denominator. So as delta Tb increases, molar mass decreases, which is abnormality. Hope you understood. If there is association, what happens? Say if you put 2 moles of any substance, in the calculation also we use 2 moles. But actually due to association, in the solution we have only 1 mole. Okay, now what happens to the molality? Due to association, number of moles decreases, so molality decreases. When molality decreases, what happens to delta Tb? Delta Tb decreases. As delta Tb decreases, M2 increases, molar mass increases. Same thing is applicable for every type of colligative properties. Here also same thing happens. Relative lowering of vapor pressure is directly proportional to mole fraction. Okay, as the N2 increases, this also increases. So as this increases, M2 decreases. Okay, remember this. So these are the abnormalities. Okay, dissociation of solute increases the number of moles. When number of moles increases, molality increases. When molality increases, delta Tb increases. When delta Tb increases, molar mass decreases, because delta Tb, or if it is depression, then delta Tf, which are in the denominator. So molar mass decreases. Now we have to correct it. If you use non-electrolytic solutes, no problem. We are getting normal molar masses. If you are using electrolytes, so then we have to correct it. So we have to correct the abnormalities. The correction terms was first introduced by a scientist named want of. Okay, he introduced a new factor which is known as I want of factor. So how to get this want of factor? There are many formulas for that. So I is equal to normal molar mass divided by abnormal molar mass. Okay, normally we are not going to use this in our study. The second one, observed colligative property divided by calculated colligative property. This is also not used widely, but this is very important. The third one, want of factor I is equal to total number of moles of particles after dissociation or after association or dissociation divided by number of moles of particles before this association or dissociation. This is important for 1 mark. See, this formula is very simple. Total number of moles of particles after association or dissociation. After by before. Number of moles of particles before association or dissociation. Remember this. Now, how to calculate the value of I for different electrolytes? Example, if sodium chloride is given, what is the value of I for sodium chloride? 1 mark question. How do you find it? I is equal to total number of moles of particles after dissociation. So how many particles will be produced? Na plus Cl minus 2. Before it is 1. So 2 by 1. I is equal to 2 for what? Sodium chloride. For magnesium sulfate also, Mg2 plus SO4 2 minus. So after dissociation 2. Before it is 1. So again want-off factor is 2. Aluminium sulfate Al2SO4 thrice. Okay, before we have 1, now we are having 5 because he given 2 moles of Al3 plus and 3 moles of SO4 2 minus are formed. So total number of moles formed how much? It is 5. So want-off factor I is equal to total number of moles of particles after dissociation is 5, before it was 1. In K2SO4, 2K plus SO4 2 minus, this is equal to 3. So next, one more example I will give you. The example of acetic acid in benzene. In benzene, it is association or dimerization. If you take 2 moles of acetic acid, after dimerization you will get 1. So here I is equal to total number of moles after association is 1, before it was 2. So I is equal to 0.5. During association, the value of I is less than 1. If association occurs, value of I is less than 1. If dissociation occurs, value of I is always greater than 1. Okay, so remember this. Next, corrections in equations of colligative properties. Now how to correct it based on the value of I? The correction is very simple. So for relative lowering of vapor pressure, we know the formula. P1 naught minus P1 by P1 naught is equal to N2 by N1. So this gives you the error during association and dissociation. So what we have to do, you put I here. You multiply all these terms by I. It's very simple, very easy to remember. Elevation of boiling point, delta TB is equal to I into KB into M, which makes the correction. Depression of freezing point, delta TF is equal to I into KF into M. For osmotic pressure, pi is equal to I into N2 RT by V. You multiply I to all those terms. You will get the correct molar mass. There is no abnormality afterwards. Okay, here this formula is important, and even the calculation of I for different types of electrolytes. This is also very important. You remember this.